All right, welcome to The Explainer. Today, we are diving deep into a topic that honestly sounds like it was pulled straight from a science fiction movie, homomorphic encryption. Now, what is it? Well, it's this incredible technology that's trying to solve one of the biggest, most fundamental paradoxes in all of data security. How can you actually use your data without ever exposing it?
So let me just ask you this. You encrypt your files, right? You use those secure websites with the little lock icon. You probably think your data is pretty safe. But what if I told you that there's a moment, a really critical window of time, where it's not just vulnerable, it's completely exposed? And that window, that's what experts call encryption's biggest blind spot. See, we've gotten really good at protecting our data in certain situations. But there is this one critical moment where it's just left wide open. And it's a vulnerability that our traditional methods, they just can't touch.
Okay, so think about your data in three basic states. First, there's data at rest. Files just sitting on your hard drive. We've got great tools for locking that down. Then there's data in transit. That's information zipping across the internet. And yeah, we're pretty great at securing that too. But the real problem, the weak link in the chain, has always been data in use. This is the moment your data is actually being processed, and it's shockingly vulnerable.
And here's the kicker. To do anything actually useful with your data, like, run some analytics or train an AI model, you have to decrypt it first. And in that one single instant, poof, it's just plain text. It's visible. It's completely vulnerable to hackers, to nosy insiders, you name it. This is the fundamental loophole that literally keeps security experts up at night.
So, what if we could slam that loophole shut? For good? Well, that's exactly where homomorphic encryption comes into play. It's best to think of it as a kind of cryptographic magic, a way to compute on data while it's still completely locked down. I mean, just think about this for a second. What if you could send your most sensitive information, your private files, your financial data, to a cloud server, have it do all the work you need, and get the results back all without that server ever seeing your raw, unencrypted data? That is the incredible promise we're talking about here. Okay, the absolute best way to wrap your head around this is with the secure glove box analogy. So imagine this. You take some really valuable materials and you lock them inside a transparent box. This box has built-in gloves, but you keep the only key. Now, you hand this locked box over to an artisan. They can see the materials through the box, and they can stick their hands in the gloves to work on them. But, and this is the important part, they can never actually touch the raw materials. They can't steal them. When they're all done, they just hand the lockbox back to you, and only you, with your private key, can open it up and get the finished product. Right? In this story, that artisan is the cloud server, and your valuable materials? That's your data. It's always secure, but still perfectly usable. So that is the core idea behind homomorphic encryption. It is this really unique form of encryption that lets you perform computations, math, directly on the encrypted data, the ciphertext. And here's the magic part. When you finally use your key to decrypt the final result, it is identical to the result you would have gotten if you had done all that math on the original unencrypted data to begin with. It's literally the secure glove box for our digital world.
But look, this incredible technology, it didn't just appear out of thin air. Not at all. It's actually been the subject of a decades-long quest, a journey to find what so many in the field have called the holy grail of cryptography.
The core concept was actually proposed way back in 1978. But for more than 30 years, it was just an idea, a fascinating but seemingly impossible theoretical dream. Then, in 2009, everything changed. A computer scientist named Gentry had this absolutely monumental breakthrough. He proved that fully homomorphic encryption wasn't just a dream, it was actually possible. And since then, it's just been an explosion of research, with each new generation of these schemes getting faster and more practical.
So the technology really evolved in stages. The first versions were what we call partially homomorphic. They could do only one type of math, like addition or multiplication, but they could do it over and over. This is actually perfect for things like securely adding up encrypted votes in an election. Then we got somewhat homomorphic encryption. This was a step up. It could handle both addition and multiplication, but only for a limited number of steps before things got, well, computationally messy. But the real prize, the ultimate goal, was fully homomorphic encryption, or FHE. And that's the whole shebang, the ability to perform unlimited operations of any kind, making it powerful enough for really complex stuff, like training an AI model on private medical records.
Okay, so how on earth did they make that final leap from somewhat to fully? Well, it was through an absolutely genius technique called bootstrapping. Think of it this way. Every time you do a calculation on encrypted data, it adds a tiny bit of computational noise, or static. Do a few more calculations, and the static gets louder and louder until you can't even make out the original signal anymore. Bootstrapping is this incredibly clever process that basically refreshes the encrypted data. It cleans out all that built-up static, making the signal crystal clear again. And by doing that, you can just keep computing forever. This was the key that unlocked the whole thing.
All right, so the theory is absolutely mind-bending. But what does this actually mean for us in the real world? What can it do? Well, this is where we get to see homomorphic encryption's true superpowers in action.
I mean, just imagine this. Multiple hospitals could pool all their sensitive patient data to train a powerful AI that can predict diseases, and they can do it without a single person's privacy ever being compromised. Or picture this. Rival banks could securely collaborate to spot massive fraud patterns by analyzing their combined but still encrypted transaction data. And look, this isn't just theory anymore. It's actually happening in systems like Microsoft's Election Guard, which can tally votes with complete privacy. This is a total game changer for secure cloud computing, for healthcare, and for meeting super strict privacy laws like GDPR and HIPAA by design.
Yeah, it is absolutely no wonder why cryptographers have called this their holy grail. I mean, think about it. It solves the one problem they've been chasing for decades. How do you make data both perfectly private and perfectly useful at the exact same time?
And this is not just some academic curiosity, okay? If you want to see where things are headed, just follow the money. The global market for homomorphic encryption is projected to shoot past $250 million by 2027. That tells you that businesses are taking this very, very seriously. They're turning what was once a cryptographic dream into a real commercial product.
Okay, but let's be real. It's not a perfectly smooth road ahead. There are still some pretty big challenges to tackle before this technology is just everywhere. But the good news is, the path forward is becoming really clear.
The number one challenge, without a doubt, is performance. I mean, doing all this complex math on encrypted data is incredibly intensive for a computer. We're talking about operations that can be anywhere from 1,000 to even 1,000,000 times slower than just doing it on regular, unencrypted data. That massive computational overhead is really the main thing holding back widespread adoption right now.
But here's the cool part. There is a massive global effort underway to solve this very problem. And it's basically a three-pronged attack. First, you have researchers designing smarter, way more efficient algorithms. Second, you have engineers building specialized hardware, custom computer chips designed for one purpose, to accelerate these calculations. And third, the community is creating common standards to make sure the tech is not only secure, but also easy for everyone to implement.
And when you put all of that together, you start to see the true paradigm shift that's happening here. For decades, our entire online security model has been based on trust. We have to trust our cloud provider, trust our apps not to misuse or lose our data. Homomorphic encryption completely flips that on its head. It replaces that with a zero-trust model. We don't have to trust anyone because we never hand over the keys to our data in the first place.
So, I'll leave you with this final thought. If we can truly compute on our data, if we can collaborate and analyze and innovate, all without ever having to reveal the raw information itself, what does the future of privacy really look like? The possibilities are just staggering. Thanks for joining me on The Explainer.